Thank you for coming to our talk. We're from Rowan University, and we're talking about the evaluation of blend time experiments in unbaffled tanks using two methods, a conductivity method and a color change. This is based on Rowan University's student work at the Rowan Engineering Clinics. And I am Robert Hesketh with AIChE, and the students will introduce themselves as they talk. So here's the presentation.
I'm Chad Cochran, and so here we're showing our lab scale. And so in unbaffled tanks, the flow is tangential and rotational, and there's little top to bottom flow, while in baffled tanks, they turn the rotational motion into axial flow. And so that's good for suspending solids, and it's good for turbulent flow. And then here in this video, we can see the solid suspension in our unbaffled tank. So why do we use unbaffled tanks? In tanks with baffles, cleaning the baffles is difficult. It requires shutting down the process and taking the time to clean them or take them out of the tank and replace them. And also we use unbaffled tanks because we want entrainment of the gas in the tank. And because of this, we track the vortex length. As you can see in the video on the side here, you can see the depth of the vortex from the original liquid height. And it's desired to not have the vortex go beneath the impeller because that entrains gas, which is a bad thing.
Hi, my name is Tim Lucius, and as you can see right here, this is a plot of Reynolds number versus power number, and the power number for unbaffled tanks is a function of Reynolds number in turbulent flow. This should happen, as you can see in the work right here, done by Zhang from the University of Dayton. And
so here we have some standard variables for mixing in tanks. And as you see here, we have a variable x for the vortex depth at the deepest point, which occurs in unbaffled tanks. So this slide is on what if the vortex depth x equals 0. And as you can see, the Froude number would become you'd have a 1 over a very low number, which would go to infinity. And so in some cases, we use the inverse Froude number, which puts the vortex depth on the top of the fraction there.
Hi, I'm Gabriel Bateman, and we're taking a look at the setup we used. The tank has an 8-inch diameter, and it's 16 inches tall with a spherical bottom. The motor is 1/5 horsepower with a variable range of RPMs, which is why we picked it. And there are also 3 different impellers, all of which are 3-inch diameter. We began testing on a laboratory scale, and in the spring we're hoping to raise the scale at Philadelphia Mixing Solutions, where we will be working with a larger tank and as well as larger impellers. This slide shows that increasing the impeller speed increases the vortex depth as well. If you take a look at the picture at 200 RPM, there's a small vortex, and as you increase the RPM, the vortex increases as well. As you can see here, there's no impact on the vortex depth based on the height of the impeller.
okay, so as you can see here in this data plot, we have a Reynolds number versus inverse Froude number, and the inverse Froude number is just a dimensionless relationship that gives you an idea of vortex depth. So if you could take a look at the speeds or the Reynolds number under 20,000, as you go lower and lower into laminar flow, you can see the vortex disappears, and then once you get past this transitional region around 60,000 Reynolds number, you can see that as you increase the Reynolds number, the inverse Froude number or the vortex depth changes less and less as you go to higher Reynolds numbers.
My name is David Siako, and this is a video visualizing mixing zones and blend time with color change. So we can see here from the video that the packet doesn't mix evenly on the outside of the tank. It'll mix a little quicker than on the impeller and in the core. So to determine blend time, we have two main ways, a conductivity measurement, which would be done with a probe, and a color change method, which is visual and done with color changing chemicals.
So here we have a visualization of how the probe acts as a baffle in the tank. This probe is being used to measure conductivity, and so you can see that the depth and the distance from the wall somewhat affects the vortex, but it doesn't completely disturb the vortex in the tank.
Okay, so one of the problems that we have here is when we add a tracer to start the experiment, there's a point where the volume that we're adding does not become negligible anymore, and that's just one of the problems that we face.
So the figure here is a parity plot that compares the data that we took at different liquid levels to the Grenville correlation for baffled tanks. So the data doesn't fit it perfectly because we're taking it in unbaffled tanks, but it does generally fit the plot, fit the trend that the Grenville correlation shows.
So one of the color change experiments that we did was we reacted an acid base, a strong acid with a strong base in the vessel using a phenolphthalein indicator, and this didn't work out very well because the pH change is dependent on ion concentration, which changes for each titration, and that makes this experiment not repeatable. So if you were going to do this, you'd have to have a clean vessel through each time. It also means that you have to use a pH probe, which is considered a partial baffle effect, and that's not going to give you great data. And also, it could become a safety issue if you're working with strong acids and strong bases.
Should I keep that in? Yeah.
So the next experiment that we moved on to after the pH was the iodine thiosulfate reaction. It's a procedure that we got and modified from the Handbook of Industrial Mixing. We made a few changes to the starch indicator, mainly that we used less of it than the original handbook, and we used less volumetric amounts of iodine and the sodium thiosulfate in the vessel for each trial run. So we add these to the tank just like the pH one, and the blend time's recorded, when the color change stops. So the video on this slide shows the original procedure from the Handbook of Industrial Mixing. It used, like I said before, the higher starch concentration, so that's why it has this really dark blue color, and it used a lower volumetric ratio. So as you can see, we really didn't get any mixing, any blend time that was visually observable.
Okay, so this is the schematic of what's actually happening inside the vessel. This is the reactions that are going on. So the iodine reacts with sodium thiosulfate, and that's going to destroy the I2 complex, which is needed to form the I3 complex that you see here in reaction 2. And this right here is actually the reaction that induces color change. And then whenever we go back and forth, you can see that when you react the Ki3 with the sodium thiosulfate, that is also going to take away color change. So the big takeaway from this is the reaction 1 and reaction 3, they take away the color change, and reaction 2 is what makes the color change to blue. Okay, so if you remember from the last slide, looking at reaction 2 was the formation of triiodide. This is actually how the color changes. When the triiodide is formed, it's able to slide into the amylose component of starch, which is the structure of it is actually a long coil, and that actually makes the iodine soluble in the vessel. When the triiodide is destroyed and it becomes back to I2, it is no longer soluble in the starch, and it changes the color from blue to clear.
So the videos on this slide show that the blend time is going to decrease as the impeller speed increases. At lower impeller speeds, we can see the mixing zones better in the vessel, that the column takes the longest to blend, you can see right now. So this slide shows two videos, same kind of test, but instead we're varying the concentration of the starch indicator. what's interesting is that it really doesn't have an impact on blend time. As you can see, the two blend pretty simultaneously. The only difference is that in the starch indicator with a higher concentration, it leaves this kind of cloudy blue tint in the end of the blend time, a trial run, which is okay. The original procedure did talk about this happening, and it's just because that high concentration of starch will leave a little bit of cloudiness in the tank. So the difference in color in the last video came entirely from the difference in concentration in starch. So all this means is that the difference in color means nothing for our videos about the difference in blend times for our data. So whether it's red or blue, it still is pretty consistent data. Yeah.
Alrighty, so on this side we have a data relationship versus impeller speed versus dimensionless blend time unit, and if you take a look at the interval from 200 to 400, it's a constant value, but when you add in the 450, the relationship starts to curve a little bit. So that's one of the things that we're really going to look into as we progress with this lab, is what is actually happening at those impeller speeds.
So now we're looking at some of the problems that we faced with the iodine thiosulfate reaction. The first one being the starch indicator has a short shelf life, and it can easily cloud the vessel solution when it becomes moldy. In addition to that, the optimum ratio of sodium thiosulfate to iodine is being investigated further. Not all the ratios have given reproducible blend times.
So the conclusions of all our work that we've done up to this point is that there's definitely going to be multiple mixing zones in the unbaffled tank, specifically between the core and the annular region near the wall. That's seen in a lot of our color visualizations. As for the conductivity measurements, we definitely determined that the probe is going to act as a partial baffle, but it's not going to totally destroy the vortex. And ultimately, it does correlate well with the Grenville equation for baffled tanks. As for the iodine thiosulfate reaction, it's definitely an effective representation of blend time in unbaffled tanks at the correct ratio of reactants. The 1 gram per 1 gram per liter starch indicator is going to give us the red color, while using a much higher concentration is going to yield that dark blue color. And you can see the mixing zones in this experiment as well. The optimum ratio that we found is 3.1, but again, from what the handbook said at 2.5 to 1, there's definitely some discrepancies in how much of each reactant you need to use, and that could be a little problem going forward for repeatability.
So some of the work we want to do in the future involves investigating the liquid level and the liquid viscosity and seeing if that has any effect on the blend time in the same tank that we're using. In addition, we want to expand the experiment to different scale tanks and possibly like a baffled tank, compare that to an unbaffled tank, and use the other impellers we have available to us and see how that compares to our already completed data. In addition, we want to compare the conductivity results with the color change results and see if the results match or how they differ.
Okay, so finally, we'd like to thank the former mixing clinic students from 2014 to 2019 that has helped us develop all of this work. We'd like to thank Philadelphia Mixing Solutions for allowing us to go in and scale up our work and see how that works with the industrial size scale. I'd like to thank my peers, my Rowan student peers, and especially I'd like to thank Professor Arthur Etchels, who has graciously donated us his time. And lastly, here are our references that we use to help develop our work, and we'd like to kindly thank all of those names who are showing up on the screen right now. Thank you all.